Hello everyone, and thank you for joining my session. My name is Krishna Munnaluru, and today I'll be talking about how we built a production-ready MLOps pipeline for telecommunications, focusing on a neural network-based voice-over IP monitoring system. This work demonstrates how AI-driven monitoring can transform carrier-grade voice-over IP operations with both high accuracy and automated deployment pipelines. By the end of the session, I hope you will see how integrating MLOps with Telecom can make networks more resilient, cost-effective, and scalable. Here is what I will cover today. First, I will describe the challenges with traditional telecom monitoring. Then, I will introduce our MLOps architecture, followed by a closer look at the neural network model we developed. Next, I will walk through the deployment strategy, showing how we ensure reliability and scalability in production. Finally, I will share the business results and the roadmap for ongoing improvements. Traditional monitoring has gaps. So let's start with the current state of VoIP monitoring. Tools only provide about 40% visibility into the network, leaving blind spots where critical issues can go. They are also reactive. It typically takes 15 to 30 minutes to detect and respond to issues. In telecom, that delay can mean thousands of dropped calls and frustrated customers. And finally, the statistical models used for quality predictions only reach around 65%. This gap is exactly why we need an AI-driven approach capable of understanding complex patterns and operating in real time. MLOps architecture overview. Our architecture brings together real-time data ingestion, feature engineering, automated training, deployment, and monitoring into a single production-ready pipeline. We use Kafka for streaming voice over IP events, Kubeflow for training, orchestration, MLflow for model registry, and monitoring through Prometheus and Grafana. The key here is that all of these components are tied together. So models aren't just trained, they are continually observed and improved. Let me highlight 4 essential components. First, real-time data ingestion with Kafka processes thousands of events per second at sub 100 milliseconds latency. Second, the automated training pipeline orchestrated by Kubeflow, which runs distributed GPU-based training with hyperparameter tuning. Third, deployment automation. We use blue-green deployment models for zero downtime and instant rollback if performance degrades. And fourth, comprehensive monitoring where custom metrics and dashboards give visibility into both model performance and system health. Together, these ensure a carrier-grade, reproducible, and resilient ML lifecycle. Our neural network combines CNN layers to extract features from packet sequences and LSTM layers to recognize temporal patterns across sessions. We added innovations like custom embedding layer for protocol-specific features, an attention mechanism to focus on anomalies, and hierarchical feature extractor across timescales. The result, 88% prediction accuracy with a 23-point movement over traditional statistical methods. That's a major leap in how accurately we can predict and preempt call quality issues. The model is only as good as its features, so we built a fully automated feature pipeline. At the edge, high throughput collectors capture SIP, RTP, and QoS metrics. These are processed in real time with Apache Beam, handling over 10,000 events per second while extracting 45 plus features. We use recursive feature elimination for automatic feature selection and Feast as a feature store to ensure consistency across training and inference. All of this is logged and monitored to maintain data quality and lineage. Training is orchestrated through Kubeflow pipelines. We use TensorFlow data validation for schema checks and drift detection, then run distributed GPU training at scale. Every experiment, parameters, metrics, artifacts is tracked in MLflow so results are reproducible. Models are versioned and registered with clear approval workflows so teams can roll forward or backward confidently. In production, system maintains 96% anomaly detection accuracy while handling thousands of concurrent requests with 99.99% availability. We achieve this with containerized models in TensorFlow serving orchestrated by Kubernetes with horizontal autoscaling. Blue-green deployments provide zero downtime and edge inference nodes across regions deliver responses in under 50 milliseconds. This is a true carrier-grade ML deployment. Comprehensive monitoring system has been developed. Monitoring goes beyond just accuracy. We track model performance metrics like precision and recall, data quality metrics like feature drift and missing values, system health such as latency and throughput. When drift is detected, retraining is automatically triggered. We also run A/B tests in production and use self-healing mechanisms for infrastructure issues. This makes the system adaptive, not just reactive. Trust is critical in telecom operations, so we have built explainability into the pipeline. We use sharp values for feature importance, counterfactual explanations to show how outcomes could change, and dashboards that track feature attribution over time. Automated model cards and audit logs document every version and decision. This means engineers can always trace a prediction back to its root cause, essential for both regulatory compliance and operator trust. What does all this mean in practice? With this system, fault detection time has dropped from 15 to 30 minutes down to 2 to 5 minutes. Network visibility is greatly improved. Licensing costs are reduced through open source tooling, and uptime has reached carrier grade levels. Most importantly, customer satisfaction improved because quality issues are caught before they affect end users. We rolled this out in phases. Phase 1, the foundation, the data collection, feature engineering, and an initial model. Phase 2 is automation, CI/CD pipelines, testing, registries, and dashboards. Phase 3 is scale, distributed training, and geographic deployments. Phase 4, ongoing optimization, ensembles, tuning, and knowledge transfer. This phased approach allowed us to deliver incremental value while building towards the full vision. To wrap up, 3 points. First, production-ready ML requires end-to-end thinking from data to monitoring. Second, automation drives reliability, especially at telecom scale. And third, it builds trust, which is essential for adoption in mission-critical systems. These principles guided us in creating a system that's not just a research project, but a reliable production-grade MLOps system. Thank you for your time. I hope this session gave you insight into how MLOps can revolutionize telecom monitoring. Thank you.